There we go. All right. So if y'all remember where we started off, where we left off, we had processor anatomical data, and as a result of that, we had white matter mass, CSF, whole brain mass, as well as transforms for the T1 to MNI space, right? And then to our functional data, we did we dropped some TRs, we conformed the data, we dropped some TRs, we did slice timing correction, we did motion correction. We used the mean EPI to calculate co-registration between the T1 and the EPI space using boundary-based registration. And then that transform we could combine with the T1 to MNI so that now we have an EPI to MNI or fMRI to MNI transform. Right? We also did denoising to remove effects of physiological noise, cardiac respiration, kind of unspecific noises, as well as motion, and discuss the global correction, right? And so if y'all remember, and we also discussed filtering, it was a part of that, and scrubbing. So if y'all remember, what we did is we fit that regression equation, right? And then we took the residuals from that. And then we may or may not have filtered it based on that. But, so I'm combining all that into denoising. So now we're going to do the individual level analysis, right? And so the individual level analysis takes that time series of ROIs and it constructs a single map from that is somehow has contrast that we're interested in for some aspect of brain function, right? So this is analogous to when you're doing individual level analysis for task fMRI, where you would do your GLM, for example. Here, the analysis might be REHO, might be VMAC, it might be a couple of different things. And we'll go through those a little bit, but first I wanted to talk about kind of how we exactly do that, right? And so there's two kind of subdivisions of the individual level analyses that we do, right? So some of the data, we take the data, the denoise data is still in subject space, and we calculate that derivative on it, right? And so the things that we calculate in original space are ALFF / FALFF, REHO, seed correlation analysis, and then this also is kind of dual regression analysis. So what are other things? Anything else, Danny?
In native space?
Yeah.
The spatial floating is not in.
No, that's not this analysis. That's going to happen. We'll show you that in a minute.
Yeah. Yeah.
All right, and so we can also extract time courses, sort of non-specific, that you could use for other types of analysis that you want. Right? And then, so that's some data we have. And so what we would do for everything except for extract time courses, because that's just time courses comes out, but we calculate the transform in native, or calculate the derivative in native space, and then we write it to MNI space. Right? And then after that, we smooth. Right? And then you're done. Okay? So the reason why we do this is we want to minimize the amount of correlation, or we want to reduce the amount of kind of artifact that we introduce into the generations of these maps. Specifically, the biggest thing that happens is that all of the steps that are done, particularly these steps, increase the amount of spatial smoothness of the data. Right? So remember when I was talking about interpolation, when you average voxels together from nearby to create a new voxel value, that smooths the data, right? And the same thing, smoothing does the exact same thing, but more intentionally, right? And so so what'll happen is that process will tend to increase the amount of correlation, so it'll make the blobs bigger, right? Which could adversely affect the spatial specificity of what you're interested in seeing, right? But what we found is if you do this stuff afterwards, it does that effect less, right? It affects it less. And all of these, the nature of the measures allow us to calculate in the original space, so we do it, right? So why do we smooth after we calculate individual analysis? So very similar to M&I, or very similar to task-based analysis, the goal of smoothing is to improve the alignment of brain regions across individuals, right? And it's also there so that assumptions regarding like Gaussian random field theory are more appropriate and can be more appropriately applied to the data. Also, it improves SNR, right? Signal to noise ratio. How it improves SNR is essentially by averaging. So all of noise, typical noise, we assume is zero mean, right? So if you average it together, then it goes to 0. And so that's what we do. And that's why we do that smoothing. So another interesting aspect is remember I said that we want to improve the kind of the function, the anatomical co-registration of these brains to one another. So the basic idea is, you know, we do all this M&I standardization, right? We transform all the data to M&I so that they should be the same, right? But, you know, kind of one of the things that assumes is that functional subunits of the brain are sort of identically mapped to structural features of the brain, like sulcal patterns of the brain and things like that. But it could actually be that there is a little bit of variation where those regions lie on the cell side, for example. So if you smooth them, then you make them a little bit bigger and you increase the potential for their overlap. But there's also another way that we can improve the degree to which they overlap. And that is when we write it to M&I space, we can write it at a higher voxel resolution, so smaller voxels than how we acquire the data, right? So what we might want to do is write to M&I space at 2 millimeter, which is what FSL does, right? Or maybe 3 millimeters, but this is something that you can specify in the pipeline. And so the basic idea, though, is that if you can imagine, say you have, you know, there's a little bit of error in your alignment to the two brains to one another. And say that the alignment is such that voxels, you could be plus or minus 1 voxel off, just in the correspondence of those two things, right? Well, so if your voxel size is 4 millimeters or 3 millimeters, then you have more error than if it's 2 millimeters. So it's just that idea is that it allows them to kind of correspond to one another a little bit better, right? So for that same reason, when we do our C correlation analysis, when we extract our C time series, we actually take the data, project it into M&I space at 2 millimeter, take the seeds, we project it into M&I space at the same resolution as your seed mask, right? Because we don't, remember, whenever you take a mask and you downsample it, make it bigger, you kind of blow it out and make it less specific, right? Anatomically specific. So we take the resting state data, project it into M&I space at the resolution of the seed masks, and then we extract those time courses. And then we take those time courses and apply them in original space, right? Back in the original space. So as a caveat to that, when you specify your seeds, if you specify them at very high resolution, you could kill yourself and kill the memory of your machine by that procedure, right? So for example, I had a colleague in my lab who wanted to have very, very, very precise seeds. So she made a seed mask that had 0.1 millimeter resolution. And as a consequence, we couldn't log into our server for a month. So the memory, so even when you do 1 millimeter, it's a lot. So maybe about 2 millimeters you want to specify your seeds, right? You probably don't need the specificity of 0.1 or 1 millimeter. So you should definitely consider that. So for example, if you just stuck in like a free surfer generated parcellation of the brain, you're going to subsample or upsample your fMRI data to 1 millimeter, right? And so that's going to require a lot of memory. So you have to be cognizant of that when you think about the types of seeds that you use in the atlases you extract with. So the, I was going to say something. Oh, so think about, so how big does it get, right? So suppose you have data that is 3 by 3 by 3, acquired at that resolution. If you sample that to 1 millimeter space, you're increasing the size of the file by 27, by a factor of 27, right? You go to 2 by 2 by 2, you're increasing it by a factor of, right, well, 27 divided by 8, right? Because you're going from 3 by 3 by 3 to 2 by 2 by 2, right? So it's not, but you see, that'll just give you a sense of how much is blowing it up, right? And so, you know, you can look at your file size just on this to get a sense how big it is. But so anyway, so that's definitely something. So I will guarantee you that if you run out of memory running out of pipeline, 9 times out of 10, it's because you're using somewhere a seed atlas that is way too fine resolution, right? And so, yeah, dual regression, I believe y'all are familiar with that. And so we can do dual regression as well. And with that, we do a similar thing where we copy to the resolution of those maps, so they should be big too. I'm sorry, similar resolution. So for other derivatives, it's actually better that we copy them into M&I space first, right? So there are some derivatives that we write into M&I. Then we calculate. So these would be VMHC, centrality, and in centrality here I'm including eigenvector, degree, and LFCD. Is there anything else that's calculated? Right? And then these are, the results of that are smooth. Now, so the reason why we do these this way is because their calculation pretty much requires it, right? So in order to do voxel mirrored homotopic connectivity, and we'll go over that in a little bit more detail in a minute, we need the brain to be symmetric. So we'll have and calculate a separate registration to a symmetric brain, then write it into symmetric space, and then do the calculation in that space. Also, centrality, different centrality measures are sensitive to the number of voxels that you include in the brain, right? To keep that consistent across all the individuals as a way to normalize that, we do the analysis in M&I space, and we use a standard template across all of the individuals for the gray matter, so that we're restricting it to gray matter, and there's always the same number of voxels in everybody's brain, okay? So another thing about centrality is we've been working a lot on this, Danny and I, in terms of optimizing it. But this was the other area where it could really blow up on you in terms of both memory and speed. So when you do centrality, you want to limit yourself to just the gray matter because it makes a lot more sense to only look at the connections between gray matter, connections between, say, gray matter and the ventricles are, you know, if they're there, they're artifact. We probably should try to avoid those. But also, they can take a really long period of time to calculate. So we want to restrict the number of voxels that we actually use in calculation. So those are those things. And so after we've done that, then we can do group analysis, right? So what I can do now is go through a little bit of these derivatives and tell you about them more. But just, are there any questions about this procedure, about why, about how, about anything? Yes?
What are your thoughts on the differences? Are there really any differences between smoothing before you do anything to the data or after the fact? Like FSL and SPM do the complete opposite. Do you have any thoughts on that?
I mean, so I do know that smoothing statistics helps, right, is a good thing. So smoothing after you have the individual maps is a good thing. So I believe that if you were to do the smoothing before, you would almost want to smooth again afterwards, right? But an important, you know, but I've always kind of been in the school, and it kind of justifies this, where you try to do as little math as you can, right, up until the calculations of these things, right? So you don't want, so the smoothing is going to blow up like your regional homogeneity. It's just going to make it a lot bigger, right? And so regional homogeneity is particularly an interesting one. But so ReHo, and this is quick, but we'll go in a little bit more detail. But if for those of you who may not know, so with ReHo, what you have is, say, let's see if I can draw a cube here. You have your cube of your, you have your Rubik's cube that's brain, right? So you have a 3x3 region, And what you do is you calculate the correlation between the center voxel and all of the voxels on the outside of that cube, right? And so we can change it. So this is a 27 cube, right? So there's 27 voxels that you do the calculation on. We can make it smaller. We can make it just the 8 cube, so it just be the centers and not all that. Yeah, just the first neighbors, right? And those are settings there. But the point is if you smooth, if your FWHM is smooth to this level, then reho means absolutely nothing, right? So then you might want to expand the cube or something, right? But essentially, so that's a good one where you don't want to, you know, maybe FALFF and ALFF would be a little bit different, right? Yeah. So some of those things you have to consider on a case by case to think about how it might affect it. But I would say that some things are going to affect you a lot more than others. Also, and it's something we're working on, I don't know if it's completely set up yet, but when we're doing the smoothing here, so it's typical that you smooth with, you know, say like a 6 millimeter full width half maximum, right? So the actual resulting smoothness of your data is going to be kind of a combination of all of the smoothness you've induced from the different procedures, right? So think about it. So say we'll call, you know, whatever, we'll use H, J, omega. What's the best way to call this? But say we just call, we got a capital S that's like smoothing that we actually do ourselves, right? So we'll call that S, right? But then there's some smoothing that's due to interpolation for copying it in space, right? There's some smoothing in here that is due to motion correction.
But do we have a way to estimate the smoothings of the manipulations that you have done before, or it's kind of almost impossible?
You can.
You can.
And that's kind of what we're getting at,
Exactly.
right? And so then there's like the smoothing that's like that, the smoothing from the MRI, right? That's actually the smoothing that's from the MRI. But maybe before the smoothing and the MRI, you have the smoothing that's actual head motion, and then the smoothing that's the MRI, right? But the point of the matter is like if you make this here 6 millimeters, and then, you know, we don't really necessarily know this one, right? But the result is going to be probably bigger than 6 millimeters, right? And the result's probably going to vary across individuals because things like head motion, the amount of head motion affects this, and that's going to be different across individuals. So rather than smoothing with the 6 millimeter, we do a smooth to 6 millimeters, right? So so AFNI does this, and it's an iterative procedure. And what you do is you calculate the smoothness of the data, you calculate the smoothness that you know the smoothness that you want, and you calculate an operator that will make it more smooth. And you do that until the data matches closely with the smoothness that you want, right? And so that's easier than just it's not easier, but it's better than just constructing a Gaussian that's 6 millimeters and then applying it.
You're assuming that you're going to have like an effective 6 millimeter.
Right, yeah.
Instead of whatever.
So our goal is to make this number what's on the outside. So for that reason, though, as well, is if you're used to using 6 millimeter smoothness, and then you look at our data, it may look like it's a little bit less smooth, right? Because the equivalent of what you're doing when applying that 6 millimeter may result in 8 millimeter, for example, right? So anyway, that's just a caveat, so you may notice that effect. Okay?
In the case of SPM or FSM, whatever, we have to end up with larger drops.
Yeah. Well, if you look at like originally SPM, they encourage you to smooth to like 12 millimeters.
Exactly, yes.
I mean, you
will find
yeah, why not gonna just, you know, you can just use like 8 millimeter voxels. Yeah. And then your SNR goes up substantially, right? So yeah, why not? You know? Okay, so now we'll go back to the slides and I can show you, or actually we'll go to the webpage, and I can go into detail a little bit more into some of these things. I kind of don't want this to take too long because I want us to get started with the hands-on. So I'm going to go a little bit fast through these, but I'm guessing that maybe many of these y'all know about anyway, so that y'all may not need too much information. So, but definitely if you feel like I'm not giving your favorite thing enough attention, stop me and I'll try to be more attentive. Okay, so again, these are going to be on the in our user guide. And so if you look here for outputs, these are the different derivatives that we calculate, right? So of course, seed-based correlation analysis is the most common thing that that is done with resting state analysis. You can put in several different seeds, and that'll be an iterable, and C-PAX will go over and calculate a separate map for each one of those seeds. And so you can put in one image file that has multiple seeds in it. You can put in multiple image files that have multiple seeds in it, and we should be able to do that. We've updated some of this to make it a little bit better, but there's some things where you can do, we can enter it into a multiple regression rather than doing it as separate regressions for each seed, which might help kind of make the maps more independent of one another. And those are some of the things for that. There's not really too much to say about that. We also, after the map after it's created, we also will transfer it, we'll do the Fisher transform to make it a, quote unquote Z-score. And then you just put in the global analysis from there. And of course the data, so the data, the outputs that you have from the data are available at multiple levels, stages of the processing, right? So if you don't want the Fisher transform, you can just find the data without it, right? If you don't want smooth data, you just go to the step before it. Or if you want to calculate the effect of smoothing, you go to the data before it, right? And so we do a pretty good job of trying to put make as much of that available as possible. So dual regression. Dual regression is a method for extracting, there's not good pictures of it, but it's a good method for extracting a network from the brain. So, if we do, for example, the default network, if we want the default network, we can robustly get it with a seed in the posterior cingulate. We might want to include a seed in the medial frontal area as well, just so that we make sure that we get both the front and the back. But we can also extract it maybe with ICA. If you wanted, but what SCA or dual regression allows us to do is to take a map of the default network such that it's extracted by ICA or from a different analysis and extract the network corresponding to that map. So what you might think of doing is just binarizing the default network you get and then calculating the average across all of those and then using that to create your default network map, right? That may be one way of doing it. But then you could think about, well, maybe not all of those voxels are equally important to the default network. And maybe there's some voxels who contribute less to it. So you want to do a weighted average of those regions. And that is what dual regression allows you to do. The reason why it's called dual regression is it's two regressions. You do one regression that is a spatial regression, right? So it's instead of doing what we typically consider in a GLM is a temporal regression, right? Where we have a template that is a pattern of time across time, and we're comparing that to a time course. Now our template is a pattern across space, and we're comparing it to each brain image, right, that we acquire. And as a result of that, you get a time course that are the beta values estimated for each one of your images, right? Each one of your fMRI volumes. And then you take that and enter it into the second regression, which is the temporal regression. So essentially you're using that time course in order to be able to go back and do a standard seed-based correlation analysis that pulls out the subject-specific idiosyncratic representation of that network, if that makes sense, right? And so we do the first thing, the dual regression, where the spatial regression is done in M&I space, and then the time course is applied in original space, right? So this comes out of fMRIB. I don't know that they have a very good publication that fully describes this, but it's become a very common thing to do. And you can do this in a multiple regression. So how I use this is I don't do ICA. Instead, I use templates that you can find from Steve Smith's PNAS paper where he looked at the correspondence of networks between resting state and task, because I think those have a really good source. And I use those to define the networks and just pull those out. And you can come up with different ways of doing that. So ALFF and FALFF So there is sort of this theory where the standard deviation of so we all know that a bold time course is not quantitative, right? So if we estimate the time course and we see that we get a number that's 16 there, that doesn't necessarily mean 16, molecules of iron or 16 molecules of oxygen consumed, or, it's not like PET where we can do quantitation like that. There are some ways of doing calibrations, but we're not 100% sure that those work, right? So the thing is you can't, at rest, you can't measure how metabolic a region is, right? You can't ask that question and just look at the mean of the signal or something and say, oh, well, this region's blowing up hot, where these other regions are pretty cold, right? So as a surrogate measure, it's been hypothesized that the standard deviation of the bold signal is related to how metabolic the region can be, right? And the idea is you need to have a lot of local metabolites or a lot of metabolism going on in order to sustain a wide range of change, right? Because if you think about it, particularly if you assume it to be symmetric, say this is baseline, this is 0, and your operating point is right here, and if it's symmetric, then as low as you can go is here. So that should be about as high as you can go as well, right? But if your operating point is up here, then your standard deviation is going to be much bigger, so it can go there. So that is the basic theory, and so this was also something that was proposed by Biswall, and he called it standard deviation. TSD or something like that he called it. I can't remember what it is. But then similarly to that, that was independently proposed by Yufeng Zhang, is the amplitude of low frequency fluctuations. So what that means is you take the variance, the power, the standard deviation, just in the band that is typically associated with the photometric activity. So between 0.001 and 0.1, right? And that is ALFF. So what they found though is that ALFF actually is highly dependent on things like UTR. It's highly dependent, and it localizes very well a lot of sources of noise in the brain. So one way, I don't know if y'all have ever seen this or done this, but one good way or easy way to identify blood vessels in the brain is take the standard deviation of PVIs in the brain, right? And the blood vessels show up really high, the ventricles show up really high. Anything that moves a lot or shakes a lot or changes a lot, the eyeballs show up really high. So you can use those standard deviation as well for those, right? So the problem is ALFF also has that same problem. Is not only do you have this kind of quasi measure of the activity in the voxels, but you also get a lot of the artifacts, the artifacts from other things in there as well. So in order to solve that, what they do is FLFF, which is fractional amplitude of low frequency fluctuations. So what they do for that is on the top you have the ALFF value that is the variance that's just in the region that you're interested in, and the bottom is the total variance that's in the entire spectrum, right? So if you're a signal EE, you would call this total power normalization. Right? And what they found is that's much more specific to white matter, or to gray matter, I'm sorry, and it doesn't have as many of the artifacts, right? But so when you do the comparison of this analysis, essentially what you're trying to see is what brain regions seem to be more active in one group than another, right? Or be whatever. That's basically the idea. It's not a great measure. It's something to look at, but I'm not a huge fan of it. So this is by far probably one of the prettiest, what? Oh yeah, there we go. This is probably by far one of the prettiest pages that we have in the C-PAX user guide. So VMHC is voxel mirrored homotopic connectivity, right? And essentially what that means is you take a voxel on the left side of the brain, you find the voxel corresponding to the mirrored coordinate in the right side of the brain, and you see how well they're correlated. Right? And what you're trying to do is identify homotopics. And then you could look at how changes in those homotopics, how those change with whatever group or other things that you have. And you can break down different brain regions based on how symmetric they are. You can look at heterotopic connections versus homotopic and all of those. But what we just look at are the homotopics. And what you can see at the bottom is that you do get a pretty good symmetric pattern. So this is an interesting method, particularly for a lot of neurological disorders that you might consider. Like I would imagine that this would probably be sensitive to stroke, any sort of bilateral thing that happens on one side, maybe even tumor and things of that nature. So you might be interested in looking at this, particularly if you think that there's any sort of restricted perfusion going on, or if there's any sort of loss of laterality. It's kind of a neat one. So regional homogeneity, again, remember I showed you that we have these different cubes where we do the different connections, and it's essentially the correlation of that center region to the regions around it. So you can imagine that, you know, say the brain is broken up into brain areas, right? So instead of the brain, like every voxel being kind of an independent functional unit, say that a functional unit is the size more of a 3 by 3 cube, right? And so you might want to be interested in how synchronous the activity is in that region as an indicator of kind of how big that regional unit is, right? And then maybe in a pathological case, you could have a kind of a loss of synchronization in an area. Again, this might be something neurologically that might work in terms of like if there's any sort of like localized lesion in the brain that may be affecting synchrony or something like that. It's kind of an interesting one. It's sort of, so it's very much, so next we'll talk about centrality. So Riho is very similar concept to centrality, except it's a very local measure of centrality. So we have network centrality. And so the basic idea with network centrality, let's see if there's kind of good graphs there right here. So, you know, with the connectome, as we described it before, you could represent the connectome as a graph, right? So you have nodes that correspond to brain areas, and then we have connections between them, right? So if I was to ask you what is the most important node in that network, how might you calculate it? One possible way is to say, well, let's look at the node that has the most connections to the rest of the brain, right? And that's called degree centrality. So with degree centrality, you go to each one of these nodes and you calculate the number of edges that come out of it, and you give it that number, right? And then you can use that information to rank the nodes based on how many connections there are. Of course, in order to do that, you need a threshold, and you only add together the edges that are above that threshold. If you don't want to apply that threshold, or even if you do, what you can do is instead of averaging the connections, you can average the weights that are associated with these edges. And that weight is the strength of the connection between the two nodes, right? That's called weighted degree centrality. That's another thing. So the basic idea from degree centrality is that you're taking and you're measuring the you're measuring kind of this number that's like the importance, we'll call it E, the importance of a brain region based on the average of all of the weights that are emanating from it. So we'll call that I. This will be average over J, right? Weight from I to J, right? You're calculating all those weights, and this is just for I not equal to J, right? So that's one way to imagine. You're just summing all the weights that are coming out of it, right? And that gives us our weighted degree centrality. If we do that, we assume that each one of these connections, the only important information about it is the weight of the connection. But maybe more important things are themselves connected to more important things, right? So maybe not only is it that you're connected to a node, but also maybe the importance of that node's connections matter, right? So that's where you get to eigenvector centrality, which is, this is also connected with PageRank centrality, or I'm sorry, PageRank, which is used for Google searches and stuff. But the idea is that now our centrality is calculated not as a weighted average of the edge weight and the importance of the nodes you're connected to, right? So that's the basic idea. The problem with this is you might notice, is it's kind of a recursive equation, right? So it's a little bit hard to calculate because you have e's on both sides. So to calculate EI, you need to know EJ, but when I was, so it's complicated in that way. But if you do a couple of manipulations, right? So say you have, so say this is X, and then this equals, I forget the actual nomenclature here, but say WX, right? So lambda X equals WX. Does anybody recognize that equation? That's the equation for eigenvectors, right? So it just happens that you can solve this equation using an eigenvector decomposition. And the eigenvector that we're interested in is the biggest eigenvector. And that uniquely solves this equation and gives us what we want. And so in order for you to find the biggest eigenvector uniquely, in order for it to be uniquely specified, your matrix has to be, of all your correlations that you use in the decomposition, has to be positive definitely, which means all the values have to be positive. So in order to do it, you either need to apply a threshold to make all the boxes positive, or you need to do some other transform like calculate the square or something like that. But anyway, this is the basic idea for eigenvector centrality. And so the degree centrality, eigenvector centrality. So now think about degree centrality is the average, so weighted degree centrality or degree centrality is the average or is the connectivity of every node to every other region of the brain, right? So in a PNAS paper by Tomasi, that was also called global functional connectivity density, right? So it's basically the idea of how much of the brain are you connected to, right? And then he proposed another measure that was local functional connectivity density. So to kind of explain this, I'll draw a kind of a silly cartoon of a default network, looking at it axially, right? So say we got something like this, and then we got this, and maybe we have like this, and then we have this in our brain. Right? So default network by Cameron Craig. Right? So if we're interested in the local FCD of this voxel right here, what we're interested in knowing is how many voxels are in this region. Right? So you want to find all of the regions that are in that local blob. Right? So you could take the map and then threshold it and then just find the region that contains the C voxel. Right? And so global functional global FCD would include all of these regions, right? But with the local, you're just interested in that. And Tomasi has shown that that's pretty sensitive to things like gender differences and other things. So it's another measure that we added in there. Okay, so there's two of them here that are a little bit more complicated, and they're not fully implemented as of right now. So we could think a little bit about them, but we don't need to go into too much detail, but they will be happening. So with bootstrap analysis of stable clusters, this was a technique developed by a good friend of mine, Pierre Bellic, and he does a lot of clustering. I've done some clustering in my life too, but the idea is for fMRI, what he'd like to be able to do is use data-driven methods to identify anatomical subregions of the brain, or functional subregions of the brain. Right? And so if you want to do that, you could take each individual's data and you can cluster it to separate it into different regions. And what you may, though, want to know after that is, so for example, here's it applied to the basal ganglia, right? So the basal ganglia here is separated into 6 regions, right? But if you wanted to do actual statistics on that, what you want to do is try to figure out what are the certainty associated with the error bars or the confidence intervals associated with that clustering, right? So what you can do is using a technique called bootstrapping, where you take a time course, the original time course of the data, and you create surrogate data where you swap around parts of the time course. You can generate other parcellations, right? Other samples of the parcellation from whatever this big hidden distribution of parcellations of the basal ganglia might look like for that individual. And then you can do that several times, say 1,000 times. And then what you can get out is of what they call a stability map. So that's here, right? Where what you see is in each of these colors is related to how stable is that voxel, how consistently is, say, this voxel here mapped to that cluster that's marked with black. So you see these things are never done, right? And these things are rarely done, and maybe there's some areas right here that are kind of, sometimes, but sometimes not, right? So now you have these statistics that are across them, and then you can use that information to either do a group level analysis or to do a comparison between subpopulations, right? Where you can say, so now if you have this information per individual, you could actually do maybe like a group level t-test analysis between populations on these statistics and see, is there a different parcellation maybe of the basal ganglia for somebody with Parkinson's disease or some other disease. So it's a little bit more complicated and a little bit harder to do and not fully supported yet, but it's something that's pretty neat and we're excited about continuing with. There's another thing that's called CWAS, which is an analog to GWAS, and this is connectome-wide association studies, right? So if you're trying to figure out the difference between two subpopulations of individuals and you're using functional connectivity, you need to hypothesize the brain regions to use for that comparison, right? So if you have a disorder that's tightly linked to a specific part of the brain, like maybe Alzheimer's with the hippocampus, then that's not so bad, right? You can directly test the anatomical hypothesis, the functional connectivity of that region differs. But what if we don't necessarily have strong hypotheses for a certain disorder and we want to generate them, right? Well, then we might want to test the connectivity of every region in the brain, right? So to do that, it's actually not straightforward how one might do that. So one way you can do it is you can construct the connectome, take the parcellation, and construct the connectome for each one of those individuals, and then do edge-wise statistical tests, univariate tests, to see if each edge in that connectome varies between groups. Right? That's one way you can do it. If you were to do that with a smaller parcellation, say if you had 200 voxels, then you would end up doing 20,000 tests, right? So that's, or 200 regions, you would do 20,000 tests. So that's a lot of multiple comparisons, but maybe it's okay because we tend to do that much with a standard task analysis anyway, right? But now say you think, well, 200 isn't really dividing the brain up that well. Maybe I want to do every single voxel. So now say if you break it down into 4x4 voxels, you end up with somewhere where 18,000, right? So the number of tests you do is n times n minus 1 over 2, right? So what that means is if you have 18,000 voxels, you're essentially doing 18,000 times 9,000 tests, right? So that's 1,000,000. 18 times 9 is 72, 162 million, I think, right? That's a lot of multiple comparisons. So there might be some smart ways to try to get around that. And so what CWAS tries to do is do that, right? So then there's the idea of, well, what if I take every voxel at a time? And at that voxel, what I do is I run, just for that voxel, I run a test to see if the whole multivariate pattern of connectivity of that voxel is different between groups, right? And then I can map that out. So for every voxel in the brain, I could write just whatever the t statistics of that comparison is, or the f statistic. And then I could map out all of the voxels whose functional connectivity profile differs between populations, right? And then instead of doing 162 million tests, I'm only doing 18,000 tests because I'm only doing one test per voxel. And that is what CWAS allows you to do. So what you do is you select one voxel, and then across all of your participants, you extract their whole brain connectivity map, right? Then you calculate a distance matrix between every pair of individuals, every pair of participants in your data set, right? And essentially, you just take the spatial correlation of them, right? And again, we want correlation to be positive definite. So we take 1 minus the correlation, and that means it'll always be positive. However we do it, we make sure it's always positive, right? And so then what we have is this matrix that contains at each location the similarity between those two. And ideally what you would see is sort of an example here where within individuals in population 1, so this is, for example, typically developing controls, they're highly similar to themselves. ADHD is highly similar to themselves, and then TDC and ADHD are different from one another, right? And so you can actually do, and essentially an F-test is the within group variance compared to the between group variance. So you do some math on this, some matrix math, and you get an F-test. So then for each voxel in the brain, you now have an F-test that corresponds to the likelihood that that voxel varies between groups, right? And then you can do thresholding to that. You can either use actual hypothesis-driven approaches for that, or you can do bootstrapping in order to calculate your null distributions. And then the regions that you have left over are the regions whose connectivity profiles differ between populations. Right? Now, one thing that you don't know is the way in which this voxel right here, if you looked at its connectivity pattern, you don't know how its connectivity pattern differs between groups. You just know that it does differ between groups, right? So then what you can do is for regions, so say maybe you could cluster these regions to identify ROIs, and then you could go back and do post hoc analyses on those ROIs, right? So in a sense, you could call it sort of like a fishing expedition, right? But it's a hypothesis generating method, right? And you see here's different examples that we showed in the original paper on this, where we're looking at differences related to the regions that are related to development, ADHD, IQ, and L-DOPA. And we tried to do this across a broad range of measures to show that it's sensitive to things that we think should be pretty big, like development, as well as things that should be kind of more subtle. There's something else to say. Oh, also, so we're showing this here as sort of a categorical analysis. You can also do, well, the development here was a regression, right? So you can also do it with a regression. This is based off a mathematical technique called MDR, which is multiple dimensional matrix regression. Something like that. That was in science a while ago, but this is a good paper too if y'all are interested in it. We're getting close to having its implementation done, but it's kind of, there is an R implementation that the Zorar has that used to work really well, and now it's very hard to get to work. Have you tried in no luck or?
No. First time I was trying to do something similar at Mata.
Yeah.
It took a long time. Then I saw this method. I tried to apply it. Yeah.
Well,
I
so
some results that I didn't trust them. Then I wrote this guy. I had something. So
have you not heard from him or?
then I know.
Oh, okay. Yeah, if you need me, I can ping you. Zorar used to work for me. Yeah, we can take care of that. Yeah, and then you can have time series. So you can use, we have a way to export time series, so you can get your time series, and you can import it into MATLAB or whatever other tool du jour, and do your graph level analysis on that. We're working on building a more robust tool set of graph level indices, but we don't have those yet. Okay, cool. And then essentially after you do these, then you would go into the group level model, specify a model, do an ANOVA or whatever type of analysis you want. We can cover some of the details of that tomorrow. I think that'll be much better done because I don't know that I need to explain a lot about the theory of the group model. I think that y'all could probably explain it a lot better to me than me to you. But anyway, so I think at this point maybe we can start hands-on and trying to do it. All right. So what's the best way to do that? I think the best way to do it is to get Danny to lead everybody. Is that cool?
Yeah.
So we'll get them to spin up an AMI, or if they're not, if they want to do it locally on their computer, do it locally on their computer. Get an AMI launch with 0.40. And then data, if you have your own personal data you'd like to use, then we can explain how to get your data loaded up. And then if you don't want to use, if you want to use some of the data that we share, then we can show that. And then configure a pipeline, tell it to go, and go have surveys while it does the hard work. Is that cool, Danny?
Yeah.
For sure.
Okay.
I already have that.
Sure.
You need to.
Yes.
He said later is better.
6:30 is better?
Yeah.
Okay.
Not even later than that. I tried to say that we should find some